So thank you very much. It's nice to know that my lecturing is good. I'll quote that. I'm going to talk to you today about some weird and wonderful exoplanetary systems that we've discovered. So what do I mean by a planetary system is akin to the solar system. So I'm not just talking about individual planets, I'm also talking about the system in which they reside. So we'll see and come back to each of these weird and wonderful pictures that I've got up here. I have to jump around a bit. So where we're going to start off with is just an introduction to the dynamics of the solar system. It doesn't really help to kind of look at the weird and wonderfulness if we don't know why it's weird and wonderful in the first place. So let's put the dynamics of our solar system in context. Quite a few of you, I hope, will have seen quite a lot of the press that was out in the last couple of weeks about the planetary parade, as it was called. Our ability to see all 7, i.e. not including the Earth, planets in our solar system up in the sky at the same time. This is quite a rare event. The next time it will happen is around about 2040. So, you know, we've had clear skies, we might not see it next time. So this was quite heavily in the news. And this picture at the top is on like a screen stretch. So you've taken like a panoramic view in order to fit them all in. But we can see a slight arc kind of forming between the planets around here. This arc is a bit more easy to see if we just look at a cartoon rather than an image, because that weird stretch of the panoramic shot of the camera isn't there. So this cartoon now has this line depicted on it. And this line is really important. So this line is called the ecliptic plane. It follows the position of the sun over sequential days of the year throughout the year. Equivalently, therefore, it's a projection of the Earth's orbit onto the plane of the sky against the backdrop of stars. So the fact that all of our planets then follow this same line, where the Earth's projection of its orbit goes onto the sky, means that we've got a coplanar system, a very flat system. In other words, our system looks like this. We've got our sun at the center, and then each of our planets are rotating around or orbiting around in an anti-clockwise fashion on their individual orbits. So we've got a very flat system. What this animation doesn't show, and what the facts that I have shown you so far doesn't also tell you, is that the sun is also rotating in the same sense. So the planet's orbits match with the sun's rotation. So what I'm going to be referring to is an orbital axis or a spin axis. So if that's not something that you're familiar with, then a spin axis is most likely kind of like understood if you think about somebody spinning like a basketball on their hand. So the spin axis of that basketball, if it's spinning on your finger, would be projected up from your finger. So that's the spin axis of that star, or spin axis of the basketball. So our spin axis of the sun points vertically up towards the ceiling. What we're seeing here is the progression of like sunspots around the surface of the sun while it's rotating. So we can see that we're kind of looking at the equator of the sun. So I'm going to be referring to the equator as being perpendicular to that spin axis all the way through. And as I said, the equator matches up with those orbital planes of our planets in our solar system. So we've got a very flat solar system, therefore. And this flatness, or this coplanarity of our solar system, has led to our solar system-inspired formation theories. Okay, so before the 1990s, where we had like no indication of any exoplanets existing around other stars, all of our formation theories about how the solar system came to be, how the sun came to be, were all based on just that one observation of the solar system. And people have been theorizing about how the solar system has formed for centuries. And our basic hypothesis about how, or theories about how the sun and the solar system came into being falls under what's called the Kant-Laplace nebula hypothesis. It's named for 2 astronomers, Immanuel Kant and Pierre-Simon Laplace. And I just want to, because it's International Women's Day and because this is my thing, put some like dates for context down the bottom. So Immanuel Kant's lifetime was between 1724 and 1804. Pierre-Simon Laplace's lifetime was between 1749 and 1827. And in their respective countries, So Immanuel Kant was Prussian. In Prussian universities, they didn't permit women to study at them until 1908, so over a century after Kant had died. And in France, where Pierre-Simon Laplace was from, they didn't permit women to study at their universities until 1880. So these men had no female peers because you couldn't go to university if you were female, okay? So that's worth to keep in context. Doesn't add to our story of our solar system, but it does kind of contribute to the story that we have of some of the people in the audience. Okay, so what was our Kant-Laplace nebula hypothesis? So this is more of a kind of like cartoon representation of the situation that we've got going on. This blue area at the top here is meant to be signifying large expanses of cool gas that exist in the spiral arms of galaxies. These are molecular clouds. This is where all of our star formation happens and all of our planetary system formation happens, because the two are linked. Within these molecular clouds, we have different forces acting, but really, or what we would say on any other day is that gravity is king, but maybe today we should honor, again, International Women's Day and say that gravity is queen, okay? So when gravity is queen, when it dominates, what we get is the collapse of that molecular cloud into different clumps. These are technical terms. Clump is a technical term, believe it or not. And these clumps are indicated by these gray spheres in here. Inside each of these clumps, we have a protostar and an envelope that's collapsing onto that protostar. Initially, we have very centrally concentrated collapse. So anything in this envelope, which is spherical, its collapse is directed under gravity towards the center of that cloud. And this is what's been indicated by these blue arrows on this schematic. But there's also other forces present within these molecular clouds, and those are rotational forces. And what happens is that during this spherical concentrated collapse, any rotation that's present is dramatically amplified. And rotation doesn't kind of produce a force acting multidirectional like gravity does. Instead, it's focused perpendicular to that spin axis that we had before. So at right angles to that spin axis. So it acts along the equator regions of this collapsing core or clump. So rather than having our centrally concentrated collapse as we did before, our combination of gravitational fields or forces that are acting towards the center and rotational forces that are acting outwards just along that perpendicular axis to the spin axis creates as a disk around our stars. So that means that any accretion onto this central protostar has to happen through this disk that exists around that star. And these disks are really important to the study of star and planetary system formation. Here, if we're studying the kind of like formation of stars, we would call them circumstellar disks or accretion disks, because those would be why we were studying them. But they are also known as proto-planetary disks, because these disks form, or are where our planets form. They have all of the building blocks to form planets in them, and so they're known as proto-planetary. That's kind of proto as in prototype, so it's your starting point of where you're getting to with your planet. And if any of you are Terry Pratchett fans, it's kind of a little bit Turtles all the way down. You know, you have a disk around your star, and you have a disk around your planets within this circumstellar disk. And so in disks that form around your planets, you also get little moons forming around your planets as well. So this is kind of like building us this basis of our Kant-Laplace nebula hypothesis. We've naturally formed a coplanar system because we've got a disk-like structure around our star. So it's natural that we'd expect all of our planets to form coplanar out of that disk. However, there was a spanner thrown in the works when we just started discovering exoplanets or planets around other stars. And just to show you like two of the systems that we found which throw this spanner in the works, I didn't name these, so don't judge me, but this system is called XO3b. Don't know why. It's just a random name. But in this system, we've got a star rotating with a spin axis as we had before, but we've got this planet on a very inclined orbit. So this is not a coplanar system anymore. And then in another system where we've got Upsilon Andromeda, that's a kind of nicer name, I suppose, than XO3b. We can't determine what the spin axis of the star itself is, But the different planets that we've observed in that multi-planet system have different orbital inclinations. So the planets are labeled B, C, and D. The star would be A, which is why the A is not used. B is then the closest in planet. We don't know what its orbit really looks like. C has this slightly squished orbit, quite close in. And then we have a really inclined orbit of the planet D. So we must have at least some misalignment between the star and the planet's orbits in these systems. So the theory that we had before, our Cantor-Laplace nebula hypothesis, we're not just going to kind of like boot it out. We're not just going to go, you don't work. We'll have to come up with something new. Instead, what we tend to do is, like theorists in astronomy, is take a long-standing theory that's been tested to, a certain degree, and if something tells us, well, it's not slightly, or it's slightly incorrect in places, there might be some more complications, we effectively take out band-aids or sticking plasters and go, okay, that'll be a fix for that area, okay? So we've got to reconcile with these sticking plasters our existing quite strong Cantor-Laplace nebula hypothesis and give it some extra effects. And broadly speaking, there's a lot on this slide, but I'm not going to go into the details of it. I can speak, if you want me to, in the questions about some of the more technicalities that I won't go into on this slide. But they're broken down into 3 broad categories. So ultimately, you've got 3 things involved during the formation. You've got your star, you've got your planet, and you've got your disk. So our 3 broad categories of theory are then broken down into those 3 sections. Is there a way for the star's spin axis to change, which would induce this misalignment? Is there a way for the planet's orbit to change? Or is there a way for that disk's plane to change before the planets have been formed or during their formation and evolution? The answer from theorists is yes to all 3, but I'm going to be biased and just focus on this 3rd category. So we're going to have a look at some of the ways in which the disk's plane can be changed. Okay. This is because it was my area of research, so I can speak more confidently on this one than I can do the other 2. Okay, so this shows some outputs from a really large simulation that one of my colleagues here at Exeter did a few years back. This is Matthew Bates' simulations of an entire molecular cloud. So he's not looking only at one system and how it collapses and how its disk evolves, but looking at the interactions of many of the different clumps that were forming in that molecular cloud, and therefore many of the stars and their disks that were forming in that molecular cloud. So looking at the top section initially, these 3 panels look at the same star and its disk, but from 3 different viewing angles. So if you imagine like a cube, you're looking from here, first of all, then from here, and then from here, okay? So in the first of the panels, the inner disk that we have looks quite edge-on, it looks quite flat, and what we imagine from a disk is that it should be circular. So if we're seeing something that looks quite just linear, then we must be seeing it edge-on. But we've got this outer ring of material around it, so we haven't just got one disk around this system, we've got 2 disks, one inner, one outer, and they are misaligned with respect to one another. If we look at the middle panel, what we're then seeing is this outer disk and the inner disk both edge on. So we've just spun round in our orientation. And then what we're seeing in the 3rd panel is the inner disk face on and the outer disk edge on. And what you might be able to see from people sitting near the front is that the reason for this misalignment is shown within this inner disk. Can anybody see how many points are in the disk? Yeah, there's 2 points. Yeah. I didn't know how clear it was. So I didn't know how much convincing I'd need to do. Yeah, so we've got 2 points within this. So this is actually a disk that's forming around a binary star. And one of those stars has been acquired by capture. It's not been formed directly at the center of that system. And the infall of that star has brought with it its disk, which was misaligned with respect to the star and its disk that it fell into. So that accumulation of its disk and all that kind of differently chaotic dynamics that would have happened has produced 2 stars at the center, an inner disk that is face on, and an outer disk that's misaligned with respect to that disk and the stars. In this second panel, or second set of panels down the bottom, instead of looking at different viewing geometries, we're now looking at different times. So again, you might be able to see that there's a time marker in the top corner of each of these panels. So we're starting on our earliest time, hopping over on the top panels, and then continuing to hop over on the bottom panels, and it's ticking forward in time. The time it's ticking forward by is a few 100,000 years. So we're taking time travel here as we're just watching this slide. Here, what we're looking at is the interactions or the results of interactions of stars that are flying by. So they're not being captured, they're not producing a binary, but they are flying by and they're affecting the dynamics of this star and its disk. So you can see that this material is initially kind of flowing from the bottom of this disk, and as it moves around in the molecular cloud, it tilts the disk. That tilt continues, just continues round, it's quite chaotic. There's some actual stellar flybys, which clears up a lot of the material around the rest of the disk. And you can see its axis continues to change as it's just existing in its natal molecular cloud. And these were all kind of ignored in that initial Cantor-Laplace nebula hypothesis. It had no need or reason to be this complicated because it already explained the things that we were observing. So we didn't need to have this complexity or this sticking plaster. There's also been other work on this area to find different ways in which we can misalign our disk with respect to our star. This is work now by Rebecca Nealon at Warwick University. So she's had a look at when we've got a disk around a star initially, but there's now a gap in this disk, similar to how we saw in the proto-planetary disk simulation earlier. So a planet has formed within this disk and carved out a gap because it's eaten up all the material in that particular orbit. And she's then thought, well, what happens in our simulation of this system if we then allow a star to fly by this disk and disrupt this system? So this middle panel is then what's happening during this disruption, and this final panel is showing the result after everything's kind of settled back down again. And what we have then is that both sets of the disk, so this inner region and this outer region, have both become tilted with respect to their initial orientation, and our outer disk is more tilted than our inner disk. Whether a gap still is present isn't clear from the image. There seems to be a bit of like a warp produced where you've got almost like a bridge between this outer disk and this inner disk now. How the star reacts to this misalignment of its disk then depends on how strong the magnetic field is of the star. It is possible that the star can kind of pull back on that inner disk and stop it from being misaligned if the star's magnetic field is strong enough. Otherwise, it's just kind of not able to kind of put a hold on the disk and will be left spinning as it was and be misaligned with respect to both the inner and the outer disk. The final example I kind of want to show of ways in which theorists have predicted that these misalignments can happen while the disk is still present is more work, again, by Rebecca Nealon. This time, what Beck does is she takes an initially flat disk, which doesn't have a gap this time, and she puts within there, or she theorizes that there may be a planet that exists in this disk that's managed to form or be kicked out into an inclined orbit. And this is what's indicated by this white dot here. So this white dot would be on an orbit that's inclined with respect to the disk, and it's shown in this figure or kind of a cartoon up in the top corner here. So we've got this inner disk, outer disk. A gap has been made just to show that in the cartoon, and we've got this inclined planet orbit between those inner and outer disk regions. And Beck has followed in these simulations that she's able to carry out what happens to the disk and how that disk reacts to the presence of that inclined planet. And if we just jump to the bottom panel, what you can see is that disk is no longer flat. It's instead got this kind of warp in it. So it's almost like a squashed S shape on the field instead. So what I would warn you all is to never trust a theorist. So we need observers to then go back to the sky and say, well, okay, our theorists have said these things are possible, but we need to go out as observers and actually try and find these things. And that's what I've spent a lot of my research time actually trying to do. Not a lot of the work that I now show is my results because it is hard to find these things. The first slide you'll see is my results, and then we'll take some results from other people who've been working in this area as well. So what I'm trying to show you is that we have observed star disk misalignments. It's just very difficult. And the difficulty is kind of shown in the work that I did do. This is taking different measurements of stars and their disks and trying to extract information about the inclinations of both of them. So if we start off just with what's plotted along the vertical axis of this figure, I'll go into the details of the figure in a moment. I'm just talking through the axes first. What we have plotted between 0 and 90 degrees is the inclination of the disk. Okay, and how do we get the inclination of the disk? Well, as I said before, a disk should be assumed to be circular. It shouldn't be possible to form an elliptical disk. All disks should be circular. Okay, so if we see, instead of having this blue circle, we see this red circle instead, we can jump between that red circle, or that red ellipse, I suppose, back to the blue circle, which we think is the underlying distribution, just by thinking of the geometry, the projection of a circle onto the plane of the sky, but inclined with respect to how we're seeing it. So we can extract an inclination from what's called the foreshortening of that narrow axis compared to the longer axis. So this is how we get these measurements out. And then the star's inclination, we have to use several different measurements. So we have the rotational velocity, which is taken from broadening of spectral lines, and this is what is indicated here as v sine I. We can get the period from the planet, from the star, sorry, and we can get the radius of the planet. Again, radius of the star, sorry, I keep saying planet. With these three quantities, we can then use a calculation just from what we know about circular motion to get a measurement of the inclination of the star. So that's our axes covered. Now, what are we looking at in the plot itself? Well, this blue line is just to indicate where something that is aligned would sit, and anything that's marked in black is in agreement, even if it's got very large error bars, in agreement with that being aligned case. Anything then that's marked in red, so this system that's marked 11, this system that marked 6, this system that's marked 3, this system that's marked 7, and this system that's marked 19, they are not in agreement with an aligned case based on this way of measuring their inclinations. But this would be seen as being an indirect method of determining the presence of misalignment in these systems. I just, however, want to focus a little bit more on this system number 19, because further work has been done on this system, and it is very likely that this system has a misalignment in it. I'm going to focus first of all on what's on this side of the page, over in all of these figures. These are observations of what's called scattered light. So this is starlight that's hitting the disk and then is being scattered back to you as the observer. So it's not emission directly from the disk, it's been illuminated by the central star. For us to be able to see that, we have to block out the light from the star because the contrast would otherwise be too large. So these white circles you see in the center aren't something that's present in the image. Those are showing the location of what's called a coronagraph. It's a very fancy way of saying that we've covered the light from the star in order to see the disk around it. It's kind of like if you're trying to see down a street and you've got bright street lights, you might raise your hand to kind of cover the light from the street lights in order to see what's in front of you. But what's significant about these images? Well, they're indicating that we've got some shadows in the rings. So if we look first of all at this top quadrant here, the illumination, the brightness, isn't consistent all the way around this circle. Instead, there's a bit of a dip in brightness over here, and again, another dip in the brightness over here. And what we see as we go through these different observations, these are all the same star and its disk, but taken at different times, different dates. We don't see the shadows being located in the same locations, same positions. It's most starkly met if you compare this one to this one down here. We've got a much lower shadow on this side, even if we've got a similar location of the shadow on this side. And you can see, I'll leave you to kind of have a look and convince yourselves that these shadows do rock around the different sides. And what's been suggested as being the reason for this is that in addition to this outer ring of disk material that we're seeing, which is indicated by this circle around here in this cartoon, and we would be an observer looking down onto it, so we'd see it in a circle. We've also got an inner disk that is hidden behind this coronagraph, which doesn't have the same height to it all the way around. Instead, the magnetic field of the star, which is shown by these blue lines here, lifts material at certain positions around that disk out of that plane of that disk, and provides extra occulting material or extra scattering surfaces, which then affect how dark the shadows appear and the locations of those shadows around onto what we're seeing in these scattered light images. And this is work that's done by Aurora Cecilia Aguilar up at Dundee and Paola Panilla at UCL in London. But again, these are kind of like indirect probes of star disk misalignment. We can also see if we kind of come a bit like rely on binary systems. So going back to, again, we've got systems where we had two stars within a disk rather than just a single star within its disk. We want to see if we've got evidence of those systems as well. And again, we do. So this is work by Grant Kennedy, again at Warwick. This is a system known as HD 98800. Again, I didn't name it, it's more of a telephone number, but it's showing a misaligned system. This system actually comprises two sets of binary stars, or it's a quadruple system. We've got an inner set of binary stars called BA and BB. Again, it's just a bit basic with the naming. And what that's doing is effectively rotating into and out of the plane of the screen as they orbit one another, which is definitely misaligned with respect to this ring that we're seeing around them, which is their disk. I should point out as well that we're no longer looking at the scattered light from these disks. These observations are taken at long wavelengths. So what we're actually seeing is the light that's been illuminated from the disk itself. So we're seeing the disk shining at these wavelengths. So this is the actual disk's light coming towards us rather than the starlight being scattered off the disk. Then if we kind of zoom out from this, we've still got that ring of material, but then we've also got this wider orbit binary, which is, again, not only misaligned with respect to that inner disk, but also with respect to the inner binary system as well. So again, weird and wonderful, complicated orbital dynamics. But it gets even weirder. So when you combine observations in scattered light and thermal emission from disks, then you can see even weirder systems. So this was work led by Stefan Kraus, who's based here at the University of Exeter, in combination with both myself and also Alison Young, who used to be here, is now at Leeds. And these are up the top, we've got ALMA observations of the disk. So what you're seeing is you've got like a bright speck, which is off-center in the center. That made sense in my head, but maybe not out loud. Then we've got a circular ring of material quite close to it, but then the outer rings of material that we've got here and here are then more squished around one of their axes. So they look more inclined. If we zoom into this inner region, we found that the result, or the reason why we've got this off-center brightness in the middle, is a result of the orbits of three stars. These observations that I took at the Chara array in Mount Wilson to trace the orbits of each of the three stars. So the stars are located at this time period. Star A is here, star B is here. They do this tightly bound, almost like spirograph pattern in their orbits. And then you have star C, which does a nice circular orbit around them. So that's their orientation. And then Stefan also got scattered light observations of the same disk, and it looks absolutely nothing like these top two images. Instead, well, maybe without the sketches that are overdrawn, it looks a bit like a chicken's head. We were kind of joking about this in group meetings an awful lot. We kind of got an eye of a chicken and then the comb of like the chicken around this side. It just became nicknamed throughout the group meetings. This is, again, a different telescope taking a scattered light image, and the kind of chicken feature isn't as prominent, but you've got one side of the disk that's illuminated and the other that's seen completely in shadow. It's not illuminated. There's no scattered light coming from it at all. And Alison spent ages doing the simulations to try and marry up this picture. And what she's kind of come up with is this cartoon representation here. So we've got stars A, B, and C in here on one orbit. We've then got this inner ring, so this circle here, which is slightly inclined with respect to their orbits. So this is what this R3 is here. We've got this arc here, which we think is this illuminated region in scattered light. That's coming from like a warp in the disk. Then we've got those two squished rings that we see in this image up top here, being here and here. So we're kind of like looking as a cross-section through everything, so our rings just look like points. Okay. However, that's a bit more difficult to figure out what you're seeing. So the wonderful people at the European Southern Observatory built us a really cool animation of the system. So what you're seeing is that inner ring of material within here. So it's zoomed in here. You've got our orbits of our different stars, and then you've got that weird and wonderful wispy material coming from the outer edges of the disk as well. So I'll just replay that so we can see the outer disk material. So we've got this warp to produce this kind of misalignment. So we've got our inner material and one bit of our outer material, and then this wider region of material out here. And they've taken artistic license a bit by kind of showing it a bit spiderwebby. The density of the dust isn't really well known, so they've just taken artistic license to make it look a bit cloud-like, a bit spiderwebby when they've done that. But it hopefully shows you the just stupidly complex picture of the system. Okay, but if we wanted to look for direct probes of misalignment, then what we have to do is not look at protoplanetary disks because they're just too far away. The resolution that we'd need to resolve the star is just stupidly small. And we just can't achieve that with current standards of telescopes and even like 10 to 20 years future capabilities of telescopes. So instead, what we want to look at is what are called debris disk analogues. So we have two debris disks in our own solar system. We have the main asteroid belt, which exists between the orbits of Mars and Jupiter. And we have the Kuiper belt, which exists beyond the orbit of Neptune. And we can see these debris disks around other stars. These stars are then much closer to us, so we can actually resolve the stars themselves. The example that I want to show you is a star called Epsilon Eridani, or EPS-ERI for short. And these are two observations of Epsilon Eridani that Rachel Rotenbacher, who's based at Yale, observed. And these are looking at star spots that are present on the Epsilon Eridani star. And at one epoch, Rachel sees that the star spot is located at this location on her model of the star. And on the second epoch, 3 days later, the star spot has moved to the edge of the star. And so the only way that she could get these results to marry up with one another is if the star's spin axis is located along this direction. So that's what's symbolized by this white feature at the top of the star. However, what had previously been published a few decades ago now by my PhD supervisor, Jane Greaves, who's now at Cardiff, was the disk of Epsilon Eridani. Now, these observations were taken prior to 1998, so they're a bit pixelated by, let's call, modern standards. But these were, groundbreaking observations of disks at the time. It shows how far we've come. These observations are again looking at that thermal emission from the disk, but our disk looks, hopefully I don't need to convince you too much, well, it looks like a capital G. So it looks quite face-on. If you imagine there being a closed loop between this segment here, it's just that the disk is a little bit clumpy. It's not as smooth, so it doesn't look like a full ring. It's kind of got a bit patchy. But the only way to marry up having a face-on disk with a star that's got a spin axis along this direction is to ultimately conclude that this star and its disk are misaligned with respect to one another. So we've got direct observations of these star disk misalignments as well. So just to summarize where we've got to, so we don't know yet how common these misalignments occur, but we do know that they exist, so that's great. Those theories that were produced to predict their existence are correct. We've confirmed them with observations, and our theories of planetary system formation have to account for the diversity of planets, well, planetary and protoplanetary systems that were being observed, okay? It wouldn't be, or it would kind of be remiss of me not to celebrate some of the wonderful, these are not weird and wonderful, these are just wonderful, women that have been involved in all of the research that I've highlighted to you today. So we've got Beck Neelan at Warwick, we've got Rachel Rotenbach at Yale in the US, we've got Alison Young at Leeds, we've got Aurora Cecilia Aguilar at Dundee, Paola Panilla at UCL, and Jane Greaves at Cardiff. So thank you very much for listening, and happy International Women's Day.